Let's take a look at the logic and the mechanics of the simple economic order quantity model. To help us preview how the EOQ model works, let's begin with a visit to Sweet D's Brownies. Kiana, Sweet D's founder and president, has decided to sell premium ice cream as a topping for Sweet D's delectable brownies. Kiana can buy ice cream at $4 a gallon from the local university dairy, which is known for making decadently rich and creamy ice cream. After doing some calculations regarding service size, she estimates she can serve the ice cream for close to $20 a gallon. She's excited about the margin she will earn. Based on demand forecasts, she expects to sell about 600 gallons per year. At first, Kiana thought she would simply buy 50 gallons every month from the dairy. However, when she met with the dairy manager, Kiana learned that the dairy charged a $90 setup or ordering fee. Kiana was ticked. That added ordering cost would really eat into her profits. After all, at $90 per order, her total ordering cost for the year would be $1,080. Undeterred, Kiana thought, what if I just order all 600 gallons right up front? Then I'll only have to pay one $90 ordering fee. Kiana, however, was quickly disappointed when she realized that the brownie shop's freezer wasn't large enough to hold all of the ice cream. She remained determined. She looked at her options. Greedy Guy's Burgers, the shop next door, had a humongous freezer. Maybe she could store the ice cream there. The bad news, Greedy Guy's owner lived up to his name. He wanted to charge Kiana $3 per gallon per year to store the ice cream. Kiana thought, wow, running a business is tough work. There are trade-offs everywhere. If I order ice cream in small quantities, the ordering costs will eat up my profits. But if I order in large quantities, the holding costs will devour my profits. Kiana wondered, how much ice cream should she order to minimize her total costs? Let's help Kiana solve her inventory problem. To calculate the right amount of ice cream to order, you want to minimize the combined order/setup cost and holding/carrying cost. To do this, you will use a mathematical model known as the economic order quantity, or EOQ model. Let's build the model so we can see how it works. To begin, we need to explicitly state our assumptions. First, you are only going to look at one product, in this case a gallon of ice cream. Second, you know your actual demand. That is, you will buy exactly 600 gallons per year. Third, your demand is constant. Simply put, you will sell the same amount of ice cream each and every month. Finally, when you need more ice cream, you can order immediately. In other words, there is no delay between when you order and when you receive the ice cream. You might be thinking, these assumptions are totally unrealistic. Of course, you're right. The good news, however, is that the basic EOQ model is robust. That means it yields reasonably good results even if your circumstances don't fit all of the assumptions. Now let's draw a picture to depict the scenario we just described. Note that the vertical line represents the order quantity, or Q. The diagonal line represents the even, consistent usage. The slope of this diagonal line represents the rate of demand, or how much inventory you are consuming. Almost magically, each order you place arrives just as you run out of inventory. Because of its distinctive look, we call this inventory pattern the sawtooth model. Let's summarize. You start out with a given level of inventory Q and sell it off at a steady rate. Just when the inventory runs out, you receive your order and the cycle begins again. Remember Kiana's question, how much should she order? Another way to say this is, what is her optimal Q? Let's compare two possible options. In option 1, you order 200 gallons of ice cream 3 times a year. In option 2, you order 100 gallons of ice cream 6 times per year. The trade-off is between ordering and holding cost. Option 1 requires that you order less frequently than option 2, but on average, you hold more inventory. What do your costs look like for each option? In option 1, the inventory will fluctuate between 200 and 0 gallons for an average of 100 gallons. Remember, your demand is constant. That means your average inventory is equal to your beginning inventory plus your ending inventory divided by 2. In option 2, your average inventory will be 50 gallons. That's 100 plus 0 divided by 2. Of course, you now have to place 3 more orders than in option 1. If we graph this classic trade-off between holding and ordering costs, you end up with a picture that looks like this. Your goal is to choose an order quantity that minimizes the total of these two costs. Focus on the green line. Now, let's translate the graph into a simple equation that you can use to calculate the optimal EOQ. To build the EOQ model, use the following notation. Your order quantity is Q, and it's expressed in units. Your annual demand is D, and it's also expressed in units. Your setup or ordering cost is K, and it's expressed in dollars. Your inventory holding cost is I, and it's expressed in percent. Your unit value is C, and it's expressed in dollars. You can calculate the holding cost per unit per year by multiplying the cost of the item C by the holding cost I. Let's denote this as H, which is expressed in dollars per year. Based on a previous discussion, the total cost of inventory is the sum of your holding and your ordering costs. Now let's take a moment to think through how you would calculate these two costs. Your order costs are equal to the number of orders you place per year times the cost per order. To calculate the number of orders, you simply divide demand by your order quantity, that is, D divided by Q. Your equation for ordering costs is thus D divided by Q times K. Your holding costs are equal to your average inventory, or Q divided by 2, times the cost of holding each unit per year, H. Your total cost equation looks as follows. You optimize your inventory by taking the derivative of the total cost equation. We aren't going to walk through the math, but we do want you to remember a very important point. The optimal order quantity occurs when your order costs and your holding costs are equal. The equation for Q is as follows. Q equals the square root of 2 times D times K divided by H. That's the square root of 2 times your annual demand times your order cost divided by your holding cost. Intuitively, what should you take away from this model? Simply put, when it costs more to place an order, you want to order less frequently. But when holding costs go up, you want to hold less inventory. Let's make one final point. This intuition tells you the secret to running a lean organization. To reduce your inventory Q, you need to reduce your ordering or setup costs. Let's bring these formulas to life by helping Kiana calculate her optimal EOQ. The EOQ is equal to the square root of 2 times 600 gallons times $90 per order divided by a holding cost of 3. Run the math and you will get 189.7 gallons. Since you can't order in partial gallons, Kiana should order 190 gallons each time she places an order. Now, let's conclude by calculating Kiana's total annual inventory costs. Let's begin with holding costs. Kiana's average inventory costs are 190 divided by 2 times $3 per gallon per year. That is $285. Let's turn to ordering costs. That is 600 gallons divided by 190 gallons per order. Since each order costs $90, Kiana's annual ordering costs are $284. Kiana's total annual inventory costs are thus $569. Did you notice that annual holding costs and annual ordering costs are essentially the same? And they would have been exactly the same if we didn't round your order quantity up. This is an important point to remember. You can double check your analysis by calculating your total annual inventory costs. If your holding costs are equal to your ordering costs, you know you did everything right.